4. Environmental geology. 5.1 Introduction. The name, volcano, is given after a small island near Sicily which was named by the ancient Romans. The term volcano is derived from Vulcan, the Roman god of fire and metalwork. The study of volcanoes is significant in the understanding of the Earth's interior. Volcanoes emit magma and gases, and the volcanic eruption process brings out molten rock material from inside the Earth to the Earth's surface. These natural processes bring about changes in the Earth's landscape. The geologic processes that give rise to volcanoes and volcanic rocks are collectively known as volcanism. Majority of the volcanoes are dormant, and there are approximately 1,500 active volcanoes. Volcanoes can be explosive and non-explosive. There are other volcanoes that alternate between quiet and explosive, i.e. the volcano at Stromboli, near Sicily. The magma composition is an important factor. Silicious or felsic magma is more viscous and volatile, rich in comparison to magma with less silica, i.e. mafic. Hence they erupt explosively when compared to the mafic magmas. Scientists estimate that at least 500 million of the total world population is at risk from volcanoes. Millions of people are vulnerable to the effects of dangerous eruptions. Therefore, it is important to improve our understanding of the volcanoes and how they work. Study of volcanoes is known as volcanology, and scientists studying volcanoes is called volcanologist. Let us now learn some definitions of volcanoes and their types. 5.2 Definitions. Volcano. Volcano may be defined as any landform that releases lava, gas or ashes, or has done so in the past. A volcano is a vent or chimney and its surrounding accumulations of volcanic material, which connects a pool of molten rock material, magma, below the Earth's surface with the surface. Volcano may appear on the surface through some fissure called fissure type, or through a single opening where it assumes shape of a cone called cone or crater type. Volcanoes are often classified by their recent history of activity as active, dormant, or extinct. 5. Environmental geology. Active. A volcano is active when it is erupting intermittently or continuously. Active volcanoes are those that have recently erupted or those that show current volcanic activity, such as the eruption of lava, release of gas, or seismic activity, i.e. Mount Helens in the state of Washington. Dormant. A dormant volcano has not erupted for a long time but can erupt again. These are the volcanoes which show eruptions with a lapse of considerable period. Extinct. An extinct volcano is that which will never erupt again. Extinct volcanoes show no signs of activity and have not erupted for long periods of time. These volcanoes may now only be the remnants of lava flows or the central volcanic pipe. Volcanism. It is the phenomenon of eruption of molten rock, magma, onto the surface of the Earth or a solid surface planet or moon, where lava, pyroclastics, and volcanic gases erupt through a break in the surface called a vent. 5.3 Distribution of volcanoes. It is important to understand the distribution of volcanoes. Based on the plate tectonic theory, volcanoes and earthquakes are not randomly distributed, but they tend to be concentrated along limited zones along the plate boundaries, figure 5.1. According to the theory of plate tectonics, the Earth's outer shell, lithosphere, is made up of 7 large and many smaller moving plates. When the plates move, their boundaries can collide, diverge from each other, or slide past each other, resulting in geological processes such as earthquakes, volcanoes, and mountain formations. Volcanoes normally occur around certain specific places of the Earth's crust. They occur in the following areas. Along subduction boundaries at continental plate oceanic plate convergence such as at Mount St. Helens. Along oceanic plate convergence such as at Japan and Philippines. Ring of fire surrounding Pacific Ocean. Hotspots such as the Hawaiian Islands mantle plumes. Spreading centers mid-ocean ridges such as in Iceland, rift valleys such as at Mt. Kilimanjaro, Africa. 6. Environmental geology. Figure 5.1 Hotspot and volcanoes. 5.4 Different parts of a volcano. A typical volcano has different parts. Typically, volcanoes are openings in the Earth's surface from which molten rock, magma, and gases escape. The main parts include the following, figure 5.2. 1. Vent. It is an opening that serves as an outlet for air, smoke, and fumes. It is a pipe-like conduit connecting the magma chamber to the surface. 2. Crater. It is a depression or a bowl-shaped geological formation at the summit of a volcano. It is connected by a vent or pipe to the magma chamber below. 3. Fumaroles. They are secondary vents on the flank of a volcano which emit steam and other gases. 4. Throat. Entrance of a volcano. The main parts. 1. Vent. It is an opening that serves as an outlet for air, smoke, and fumes. It is a pipe-like conduit connecting the magma chamber to the surface. 2. Crater. It is a depression or a bowl-shaped geological formation at the summit of a volcano. It is connected by a vent or pipe to the magma chamber below. 3. Fumaroles. They are secondary vents on the flank of a volcano which emit steam and other gases. 4. Throat. Entrance of a volcano. The part of the conduit that ejects lava and volcanic ash. 5. Conduit. It is an underground passage through which the magma flows. 6. Magma chamber. It is a reservoir of magma in the Earth's crust where the magma may reside temporarily on its way from the upper mantle to the Earth's surface. 7. Caldera. It is a crater more than 1 kilometer in diameter, formed at the summit of a volcano when lava is drained from an underground magma chamber, causing the summit of the volcano to be unsupported, and to collapse. 7. Environmental geology. 8. Pit crater. They are collapse features on the flanks or summit of a volcano that are smaller than the main caldera at the summit of a volcano. 9. Lava flow. This is sheet of molten or solidified lava. 10. Sill. This is an intrusive body of magma that pushes its way between layers of sediments. 11. Ash cloud. It is a cloud of volcanic gases, ash and dust that form during an explosive volcanic eruption. 12. Secondary vent. It is vent that connects to the secondary cone for the lava to flow. Figure 5.2 Parts of a volcano. 5.5 Volcanic eruption process. A volcanic eruption occurs when pressure from gases and steam within the magma build up sufficiently to fracture the surface of solid rock. This allows lava to flow onto the Earth's surface. 8. Environmental geology. When fractures occur within the Earth's crust, then the pressure on the magma becomes less, and the magma is pushed up to the surface through the crack. When magma reaches the Earth's surface, it is referred to as lava. Successive eruption of hot, molten matter forms a cone-shaped mountain of lava. The process produces igneous rocks but may also help form metamorphic rocks due to the heat along with the eruptions. The viscosity of the magma is controlled by its acidic, intermediate or the basic nature. If the lava is acidic and rich in silica, it will harden and set quickly. Such volcanoes erupt violently and are called composite volcanoes. Some examples are Mount Etna in Sicily, Mount St. Helens in the USA and Mount Vesuvius in Italy. Basic lava which is low in silica but rich in iron content flows freely and sets slowly. Such volcanoes are called shield volcanoes. Some examples are those in Hawaii. Stratovolcanoes are built over many thousands of years after dozens of eruptions. Volcanic eruptions result in bringing new rock material from the interior of the Earth to the Earth's surface. These rocks help in the formations of mountains and islands. Further, the gases and volatiles emitted have contributed to the Earth's atmosphere and oceans. 5.6 Kinds of volcanic eruptions. As discussed earlier in the chapter, volcanic eruptions can be of two types, explosive and non-explosive eruptions. Let us now learn about this in the following paragraphs. 1. Explosive eruptions. They occur due to the presence of high gas content or volatiles in highly viscous magmas. During these eruptions, magma is fragmented into clots of liquid that cools down and become sand-sized particles. These solid particles become pyroclasts and tephra or volcanic ash. Other fragments released include blocks and bombs named according to the angular and aerodynamic shapes. Lapilli are those that consist of mostly gas bubbles. They can also be released resulting in a low-density highly vesicular rock fragment called pumice. Volcanic gas clouds and ash can rise up to 45 kilometers into the atmosphere. 2. Non-explosive eruptions. These eruptions occur when the magmas are less viscous and contain less volatile matter. When the viscosity is low, these eruptions start with fire fountains as a result of release of dissolved gases. When the gas content is low and the viscosity is high, then lava will produce. 9. Environmental geology. A volcanic dome. Lava flows result on the surface of Earth. When the volcanic eruption is submarine, then pillow lavas are produced. Mount St. Helens, Montana, USA 1980 resurgence after 123 years. Mount St. Helens was dormant for 123 years. It again erupted on the 18th of May 1980 resulting in damage exceeding $800 million. Gas and ash-filled steam came out from the mountain at a speed of around 670 miles per hour. The eruption destroyed 6 million trees. The volcanic explosion was equivalent to 500 small atomic bombs. There were 34 deaths, 10,000 animals were dead and 15,000 acres of forest land was destroyed. 5.7 Factors controlling volcanic eruptions. Let us discuss in detail about the different factors that control volcanic eruptions, in the following paragraphs. Magma composition, temperature and viscosity. Viscosity is the resistance to flow and it depends primarily on the composition of the magma and its temperature. This parameter is of utmost importance in determining the eruptive behavior of magmas. The magmas with higher silica content have higher viscosity than those with lower silica contents. Granitic or sialic magma is more viscous than basaltic or mafic magma. The shapes of volcanoes also depend on the viscosity of the magma. For example, basaltic lava forms flat shield volcanoes. Gases are not easily released from viscous magmas. Here, the pressure builds up and leads to violent explosions. These are typical of stratovolcanoes. 10. Environmental geology. Characteristics of magma. They control the kind of eruption that would take place. Magma types. Types of magma are determined by the chemical composition of the magma and three broad general types are recognized. Basaltic magma contains CO2, 4555 Wt%, are high in Fe, Mg, Ca, and low in K, Na. Andesitic magma contains CO2, 5565 Wt%, and are intermediate in Fe, Mg, Ca, Na. K. Rhyolitic magma contains CO2, 6575%, are low in Fe, Mg, Ca, and are high in K, Na. Volatile content in magmas. The explosive character of magmas is due to the presence of gases. In the Earth, at depths, all magmas contain gas dissolved in the liquid form. When the magma rises to the surface of the Earth, the gas forms a separate vapor phase due to decrease in pressure. The composition of the gases in magma include mostly water vapor, carbon dioxide, trace amounts of sulfur, chlorine, and fluorine. The felsic or rhyolitic magmas have higher gas contents as compared to the mafic or basaltic magmas. This is because the amount of gas present in magma is related to the chemical composition of the magma. For example, basaltic lava forms flat shield volcanoes. Gases are not easily released from viscous magmas. Here, the pressure builds up and leads to violent explosions. These are typical of stratovolcanoes. Magma temperature. They are characterized by different temperatures. Geological field observations and scientific measurements suggest that the eruption temperature of various magmas can be different. Basaltic magma can range between 1000 to 1200 OC. Andesitic magma can range between 800 to 1000 OC, and rhyolitic magma can range between 650 to 800 OC. 5.8 Products of volcanic eruptions. The products of volcanic eruptions include the following: lava flows, pyroclastic debris, ash, dust, gases and nuae ardentes. In addition to the gases that come out of volcanoes, large amounts of solid materials are also ejected. The smaller particles of dust reach the highest levels in the atmosphere. For strong vertical eruptions, dust can be propelled up into the stratosphere, above 17 kilometers. At 11. Environmental geology. Such heights, the suspended dust particles can block solar radiation, effectively by heating up the stratosphere while the lower troposphere cools, causing short-term effects. 1. Solid. The solid material of different sizes is ejected out of volcano during eruptions. They are called as pyroclastic material. These materials of varying sizes and grades are known differently based on their size, viz. volcanic bombs, lapilli or cinder, volcanic ash and volcanic dust. 2. Liquid. The most important product of volcanic eruption is magma. It is molten rock material consisting of mineral melt. It is. On average, the temperature of magma ranges between 1000 degrees and 1200 degrees Celsius. Molten rock material below the surface is called magma, and when it comes on the surface it is called lava. On average, the temperature of magma ranges between 1000 degrees and 1200 degrees Celsius. Molten rock material below the surface is called magma, and when it comes on the surface it is called lava. It can be felsic, viscous, or basic, less viscous or fluid. 3. Gases. Water vapors form one of the most important part constituting of the total volcanic gases. These water vapors may come from the original magma or due to boiling of underground water in the volcanic area. Volcanic gas samples contain water, 70%, carbon dioxide, 15%, and nitrogen, 5%, along with sulfur dioxide, hydrogen sulfide, carbon monoxide, hydrogen, hydrochloric acid, and methane, chlorine and argon. 5.9 Hazards associated with volcanoes. Do you think there can be hazards accompanied with volcanic eruptions? Yes, there are. So volcanic hazards are classified into primary and secondary hazards. 1. Primary volcanic hazards. Lava flows are usually not very dangerous. They move slowly and can damage property. Again, there can be a few exceptions. For example, at Zaire in 1977, the Nyiragongo volcano had a side fissure which drained the lava lake in the main crater very rapidly. It resulted in the lava squirting out at 60 miles per hour. This volcanic activity caused approximately 1,000 fatalities. Violent eruptions and pyroclastic activity. They are the most dangerous as they can travel rapidly. Hot pyroclastic flows result in suffocation, burns and death. Ash falls. They characterized by mud ash and gases. An example is the 79 AD eruption of Mt. Vesuvius causing 12. Environmental geology. About 20,000 fatalities. Nuae ardente. They are fast-moving flows of gas and magma, in a volcanic avalanche. These can be deadly due to fast flows and destructions. An example to cite is the 1902 eruption of La Soufriere, St. Vincent, which killed 1,500. Nuae ardentes consist of clouds of volcanic gases and pyroclastic debris that avalanche down the side of a volcano. They can reach speeds of almost 200 kilometers per hour. A nuae ardente from Mount Pelee, on the Caribbean island of Martinique, killed 28,000 inhabitants and destroyed the town of Saint-Pierre in 1902. Gas emissions. They accompany every volcano. Some of the gases include hydrogen chloride, hydrogen sulfide, hydrogen fluoride, and carbon dioxide. The eruption that occurred at Iceland in 1783 at Mt. Laki had a massive flux of sulfuric and fluorine gas, which killed great numbers of livestock. This resulted in a famine leading to 10,000 fatalities. 2. Secondary and tertiary volcanic hazards. Agricultural catastrophes are secondary consequences of the widespread devastation of volcanic eruptions. These hazards are varied and clearly not easily controlled. Lahars are volcanic mudflows, typically resulting from eruption under ice and snow at the summit, which mixes with the ash to make fast-flowing muds. Tephra falls. Volcanoes can emit huge quantities of loose, unconsolidated tephra that are deposited on the landscape. They can be removed using water from the melting of snow or ice during the eruption. They can also be removed by emptying of crater lakes during an eruption or due to rainfall. They can also result in roof collapse. Although tephra falls cover an area in the same way as snow, they are very destructive in nature. This is because these deposits have a density twice than that of snow. They also cannot melt like snow. They devastate vegetation, crops, and kill livestock. They bring about a loss in agricultural activities for years after an eruption. Debris avalanches and debris flows. Volcanic mountains can steepen over time. Such steep slopes may become unstable. It can result in sudden slope failures resulting in landslides or debris avalanches. For example, let us see the eruption of Mount St. Helens at Washington that occurred on May 18, 1980. The eruption of a debris avalanche was triggered by a magnitude 5.0 earthquake. This avalanche removed the upper 500 meters of the mountain and flowed into the Spirit Lake. It raised the lake's level by about 40 meters. It then moved to the west. 13. Environmental geology. Filling the upper reaches of the North Fork of the Toutle River Valley. Debris avalanches, landslides, and debris flows do not always occur with a volcanic eruption. Some documented cases of such occurrences have been reported where no new magma has erupted. Flooding. Drainage systems can become blocked by deposition of pyroclastic flows and lava flows. These can create temporary dams that could get filled with water and fail, resulting in floods downstream from the natural dam. Volcanoes in cold climates can melt snow and glacial ice. This can rapidly release water into the drainage system and possibly cause floods. Tsunami. They occur when eruptions displace ocean water. Debris avalanche events, landslides, caldera collapse events, and pyroclastic flows that enter water bodies can generate tsunamis. In 1883, the eruption of Krakatoa volcano triggered several tsunamis by pyroclastic flows entering into the sea and by collapse accompanying caldera formation. This tsunami killed 36,400 people, some even 200 kilometers away from the volcano. Volcanic earthquakes and tremors. Earthquakes usually precede and accompany volcanic eruptions, as magma intrudes and moves within the volcano. Although most volcanic earthquakes are small, some can be large enough to cause damage in the area immediately surrounding the volcano. Others can trigger landslides and debris avalanches. Volcanic tremors can also occur. This is the continuous rhythmic shaking of the ground due to moving magma underground. Atmospheric effects. Short-term effects on climate are caused when huge quantities of tephra and volcanic gases are released into the atmosphere. Volcanic ash can cause reflection of solar radiation, which results in cooler temperatures for several years after a large eruption. For example, the eruption of Tambora volcano at Indonesia in 1813 was the largest recorded in history. The year later, the area was known as the year without summer. Volcanic gases like carbon dioxide are greenhouse gases that retain heat in the atmosphere. During the mid-Cretaceous period, the carbon dioxide content of the atmosphere was 15 times higher than modern times. This could be as a result of voluminous eruptions of basaltic magma on the seafloor. The average temperatures were also around 10 to 12 °C warmer than the present times. Famine and disease. Another effect is the widespread damage to crops and livestock. This 14. Environmental geology can also lead to famine and disease. The volcanic eruption of Mt. Pinatubo, Philippines, 1991. On the 9th of July 1991, the 1,463 meters dormant volcano near Subic Bay, Mount Pinatubo, Philippines became active after 6 centuries. It resulted in a series of eruptions which lasted for months. This massive eruption was the largest on record in the Philippines and in the world since Krakatoa erupted at Indonesia in 1883. The eruption spewed billions of cubic meters of magma, gases and ash from a 3-kilometer-long crater near the mountain's summit. The explosive force ejected enormous clouds of ash and gas vertically to an altitude of approximately 40 kilometers. The ash settled deep on the ground over huge areas, up to hundreds of kilometers away. On the 17th of July, the sky was totally black as far south as Manila, i.e. 85 kilometers away. A continuous rain of pumice pebbles and ash occurred along with thunder and lightning from a tropical storm. This alternated with brilliant orange flashes from the volcano. Numerous earthquakes were also recorded resulting from Pinatubo's violent eruptions. The bulk of its eruptive energy was directed vertically upwards, so it did not produce large pyroclastic and molten lava flows. The secondary effects caused loss of life and property. This occurred a week later due to heavy rains from Typhoon Brendan. Mud flows wiped many foothill villages and forced thousands of people to flee from their homes. Scientists estimated that Pinatubo's eruption added more aerosols than all anthropogenic greenhouse gases since the Industrial Revolution. Further, a reduction of up to 1 degree Celsius in the Earth's average temperature was recorded by NASA satellites within a year of the main eruption, and this cooling effect persisted for about 2 years. 5.10 Prediction and mitigation of volcanic eruption. Volcanic prediction is difficult, but on a comparative scale it is more viable than for earthquakes. The major challenge is that every volcano has a unique behavior, which must be characterized on a case-by-case basis. This is challenging because of the long period of repose between explosions. Most volcanic predictions are based on various phenomena. 15. Environmental geology. 1. Behavior of the volcano. 2. Earthquake activity, tracking the ascent of magma. 3. Deformation of the ground surface. 4. Changes in the gas chemistry and temperature. For some volcanoes, the statistical behavior can be characterized if there is a history of 10 to 20 eruptive sequences. There is no simple physical theory for the eruptive cycle, and this is an empirical approach. Statistical methods give gross probabilities, but not short-time prediction. Individual volcanoes differ in the reliability of earthquake precursors, and again each volcano should be characterized. Inflation of the magma chamber below the volcano causes tilting and uplift of the surface, which can be measured. This is the direct result of ascent of magma and buildup of gas pressure. There are many instances of successful prediction of major eruptions. 1. Long-term forecasting. Understanding the geologic history of a volcano is important in order to assess the types of hazards posed by the volcano and also the frequency at which these hazards occurred in the past. Then volcanologists make forecasts as to which areas surrounding a volcano would be subject to the various kinds of activities if they occur in future. They also make forecasts about the long-term likelihood of a volcanic eruption in the area. Scientists examine lava flows and other deposits of various eruptions which help to the past nature of a volcano. Further radiometric age dating of the deposits and the past frequency of events can be determined. This information is extended for preparing volcanic hazard maps. This is of help to scientists, public officials, and the general public to plan for evacuations, rescue and recovery operations. They also help delineate zones of danger expected from the hazards. 2. Short-term prediction. It involves monitoring the volcano to determine when the magma is nearing the surface. It also involves monitoring for precursor events that often signal a likely eruption. Monitoring seismic waves. Seismic waves are generated by both earthquakes and explosions. 16. Environmental geology. S waves cannot pass through liquids, so arrays of seismographs can be placed around a volcano and small explosions can be set off to generate seismic waves. In case a magma body exists beneath the volcano, then there will be a zone where no S waves arrive. This is known as an S wave shadow zone. Monitoring the movement of the S wave shadow zone can help recognize the position and movement of the magma body. As magma moves and deforms rocks, it may generate earthquakes. So, there is usually an increase in seismic activity prior to a volcanic eruption. In this way, the movement of magma can be tracked. In addition, volcanic tremor is also an indication that magma is moving below the surface. Changes in geophysical signatures. Rocks contain minerals such as magnetite that are magnetic. These minerals generate magnetic field. However, above a temperature called the Curie temperature, these minerals show no magnetism. So, if a magma body enters a volcano, the body itself will show no magnetism. If it heats the surrounding rocks to temperatures greater than the Curie temperature, about 500 OC for magnetite, the magnetic field over the volcano will be reduced. Thus, by measuring these changes in the magnetic field, the movement of the magma can be tracked. Rocks have resistance to the flow of electrical current, which is dependent on temperature and water contents. When magma moves into a volcano, the electrical resistivity will decrease. Measurements of the electrical resistivity can allow tracking of the movement of magma. As magma approaches the surface, the amount of surface heat flow will increase. These small changes are measured using infrared remote sensing. Changes in ground surface. As magma moves into a volcano, the structure may inflate, causing deformation of the ground surface, which can be monitored. Some instruments, like tilt meters, measure changes in the angle of the Earth's surface. Changes in groundwater system. As magma enters a volcano, it may cause changes in the groundwater system. It can result in the water table to rise or fall and the temperature of the water to increase. These changes can be monitored. Changes in chemistry of gases. The composition of gases emitted from volcanic vents and fumaroles generally change just before to an eruption. 17. Environmental geology. In conclusion, no single event can be used to predict a volcanic eruption. Many events are usually monitored and examined in totality. Each volcanic eruption is unique, and until specific patterns are recognized for an individual volcano, predictions vary in their reliability. 5.11 Natural service functions of volcanoes. Volcanic processes have been responsible for outgassing of the Earth to help produce both the atmosphere and hydrosphere. You have read about the destructive effects of volcanism. Now let us discuss the constructive effects of volcanism. Volcanism renews the soil. The soils around active volcanoes are very fertile. The lavas produce fertile soil after weathering, being derived from virgin materials, e.g. soils in Java and black soil in Central and South India. Precious and semi-precious stones are found in volcanic rocks, e.g. diamonds are found in India and South Africa. Ores and mineral deposits are extensively produced by volcanism and related processes. Hydrothermal processes associated with volcanism produce rich ore deposits. The heat rising around magma bodies can be utilized to produce geothermal energy. Crater lakes and caldera lakes are formed, which provide source of fresh water to us, e.g. Buldana Lake in Maharashtra. The volcanic rocks also provide an abundant local source of materials for landscaping, construction activities and road building. Some volcanoes also provide us natural laboratories for observation of some of the natural processes occurring below the surface of the Earth. SAQ 1. Describe the factors controlling the volcanic eruptions. 2. How can we predict volcanic eruptions and mitigate volcanic disasters? 3. Write short notes on beneficial aspects of volcanism. 5.12 Summary. In this unit we have studied about volcanic eruption processes, the structure of a volcano, their types, effects, impacts, and forecasting the events. Volcanic eruption processes rock our planet. They lead to the formation of new rock material and fertile soils. They are also natural scientific laboratories where extensive studies can be carried out for understanding the interior composition of our Earth and for other geological studies. 18. Environmental geology. Module 07. Glaciers. Objectives. 5. Understand glacier and differentiate the different types of glaciers. 6. Describe glacier formation and glacier movement. 7. Understand glacial budget and mass balance. 8. To study different types of glacier landforms. 7.1 Glacier. Glacier is a mass of surface ice on land and formed by accumulation of snow. Glaciers flow downhill under gravity due to its own weight. Glaciers are maintained by accumulation of snow and melting of ice. The melted ice discharged into the lakes or the sea. Glaciers grow and shrink in response to the climate change. Meyer, 1974, provided a definition of a glacier. A glacier may be defined as a large mass of perennial ice that originates on land by the recrystallization. Glacier is a mass of surface ice on land and formed by accumulation of snow. Glaciers flow downhill under gravity due to its own weight. Glaciers are maintained by accumulation of snow and melting of ice. The melted ice discharged into the lakes or the sea. Glaciers grow and shrink in response to the climate change. Meyer, 1974, provided a definition of a glacier. A glacier may be defined as a large mass of perennial ice that originates on land by the recrystallization of snow or other forms of solid precipitation and that shows evidence of past or present flow. The definition is not precise, because exact limits for the terms large, perennial, and flow cannot be set. Except in terms of size, a small snowpatch that persists for more than one season is hydrologically indistinguishable from a true glacier. One international group has recommended that all persisting snow and ice masses larger than 0.1 square kilometers, about 0.04 square mile, be counted as glaciers. Hence, in the absence of an agreed-upon upper size limit for glaciers, a body of ice as large as the Antarctic ice sheet, slightly smaller than the conterminous United States and Europe combined, could properly be considered a glacier. Important facts about glaciers. Glaciers store about 75% of the world's fresh water. Glacier ice crystals can grow to be as large as baseball. 4. Environmental geology. The largest glacier in the world is the Lambert-Fisher Glacier in Antarctica. Ice is a mineral as it possesses a definite chemical composition and atomic structure, and non-metallic inorganic and crystalline. Drury, 1986, page .1. Selected mechanical and thermal properties of ice are shown in Table 1, Drury, 1986, page .2. Property units symbol quantity mechanical. Environmental geology. Latent heat fusion, KJ. A. Surface melting. B. Dissipation of mechanical heat. C. Geothermal heat. D. Groundwater flow and surface runoff. E. Liquid precipitation. The blue color of glacial ice. Snowfall covers the surface and forms a layer of snow. Every year, snowfall makes layers and create pressure on the older layer beneath. As the time passes, the low-density snow transformed into much denser solid ice. Due to compaction, pressure melting, as ice melts at OOC at atmospheric pressure, but under high pressure melts at a lower temperature, and refreezing reduce the air in the frozen mass and increase materials density. As the density of ice increases, it reflects the more short wavelength of light, i.e. blue part of the spectrum. Source James Peterson, 2011, p. 394. Area covered by glaciers. Table 1. Approximate worldwide. Six. 7.2 Glacier formation. Glaciers are masses of flowing ice that accumulated over a period of time, and the snowfall is more than the melting of ice. The formation of glaciers starts when snow remains in the same area for a year and when enough snow accumulate and transform into ice. When a snow falls, it's hexagonal ice crystal and called snowflakes, having a density of about 0.1 grams per cc, 0.06 ounces, in 3, as shown in Image 1. 7. Environmental geology. Image 1. Formation of glacial ice. Each year a new layer of snow is added and this layer compresses the older layer. The snowflakes are transformed into granular snow by melting and refreezing. With time, the grains grow and the air pockets between them decrease and become more compact, as well as an increase in density. Due to the melting, refreezing, and pressure caused by new snowfall, the granular snow is converted into firn. The firn formation takes place after about 2 winters. Over a period of time and due to pressure, partial melting, and refreezing, the ferns grow together into larger interlocked ice crystals. When the ice crystals are more compacted and very little amount of airspace left between them, they are called glacial ice. The firn is about 2/3 as dense as water, but the density of glacial ice is becoming 0.9 grams per cc, 0.52 ounces, in 3. So, from snow into glacial ice, there is a lot of transformation, as shown in Fig. 1, an increase in density. Glaciers are formed when snow remains in one place for a longer time and face many transformations. Glaciers' size varies from a small football field to hundreds of kilometers long area. Glaciers are mostly present in polar regions like Antarctica, Greenland, and the Canadian Arctic, and occupy nearly 10% of the world's total land area. Source NCDC glaciers. Accumulation and ablation are two most important terms in the formation of glaciers. Accumulation area is the area where snowfall is accumulated, usually. 8. Environmental geology. Higher elevation and ablation area, usually lower altitude, where melting and evaporation takes place. Mostly the accumulation takes place in winter and ablation part takes place in summer. The glacier is in equilibrium when the snowfall equals snowmelt. When this equilibrium is disturbed either by excessive snowfall, called advances, or by excessive melting, called retreats. The glacial system is controlled by frozen precipitation and freezing temperatures. 7.3 Glacier movement. Glaciers flow downhill due to the gravitational force generated by their own weight. Glacial velocity depends upon the thickness of glacier, temperature, bedrock, and gradient. Movement takes place by one or combination of following 3 processes. Source. 1. Internal deformation. Glaciers have ice crystals, and when there is slippage within or between ice crystals leads to glacier movement. The base having highest pressure and maximum deformation takes place at the base. 2. Basal sliding. This involves the sliding of a glacier over its rocky base. The basal sliding is of 3 types: basal slip, enhanced basal slip, and regulation slip. 3. Bed deformation. This is movement accomplished by the deformation of soft sediment or weak rock beneath a glacier. A study conducted on the glacier movement in 1948 on the Jungfraufern Glacier found that the ice near the surface is rigid and brittle. When the glacier flows rapidly at a location, friction creates giant cracks called crevasse. Image 2. Moraine is another common feature of the glacier when it pushes or carries rocky debris as it moves. There are different types of moraine, like medial moraine, run down the middle of the glacier, lateral, run down along the edges, and terminus moraine, found at the terminus or snout of a glacier. Below the brittle zone, due to weight of the overlaying ice, the ice start flowing instead of breaking. This zone is called plastic zone and ice flow in this zone. 9. Environmental geology. Image 2. Crevasse on the Easton Glacier in the North Cascades. Source. 7.4 Types of glaciers. Different type of glaciers. Alpine glaciers. Alpine glaciers are found in mountain terrain and where the precipitation and temperature conditions present due to high elevation. Alpine glaciers occupy valleys usually that was created by steam erosion. In alpine glaciers, mass flow takes place downslope because of its own weight and gravity. Alpine glaciers created the characteristic rugged scenery, like the Himalayas, Sierra Nevada, Andes, and the Alps. The largest alpine glaciers are Alaska and the Himalayas. Alpine glaciers have two zones: zone of accumulation and zone of ablation. The zone of accumulation is the colder, snowier and upper portion of the glaciers where accumulation exceeds ablation, while the zone of ablation is warmer, downslope portion, where ablation exceeds accumulation. The dominant accumulation season is winter and dominates ablation takes place in 10. Environmental geology. Summer. The equilibrium line in an alpine glacier is decided by accumulation and ablation. There are different factors which affect the equilibrium line like temperature, the interaction between latitude and elevation, amount of insolation, wind. Depending upon the climatic condition, like more snowfall shifts the equilibrium line drop in elevation, while in a warmer climate it retreats to a higher elevation. The ice movement in alpine glacier takes place from the zone of accumulation to zone of ablation. Continental glaciers. Continental glaciers exist where the appropriate conditions for ice formation occur because of high latitude. Image 3 shows continental glacier. The continental glacier is much thicker in the central part and thinner from the edges. The continental glaciers are larger than the alpine glaciers. About 96% of glacier area is occupied by ice sheets of Antarctica and Greenland. In continental glaciers, the ice and ice caps flow radially outward and downward in all directions from thicker side to thinner side. So, the zone of accumulation is the central part and zone of ablation is the surrounding. Image 3 Continental glaciers. Calving Glacier. Calving Glacier has a terminus that ends in a body of water, river, lake, ocean. Into and lose mass by calving means breaking off mass from main glacier and form icebergs. 11. Environmental geology. They are widely distributed and fast-flowing. The correlation is linear between the calving rate and water depth. The calving glaciers are significant because of glacier dynamics, non-climatic behavior, and socio-economic impacts. Niche glaciers, developed in small couloirs or depressions. Niche glaciers are very small in size. Such glaciers occupy gullies and hollow on the slopes and appear as little more than large snowfields. They do not make image of a typical glacier. A niche glacier may develop into a Corey, cirque glacier if conditions are favorable, and it is common in glaciated areas to find small niche glaciers between larger Corey, cirque glaciers. Source: Encyclopedia of Snow, Ice and Glaciers. Source, page .779. Cirque glacier. Cirque glacier is a small glacier that forms within a cirque basin. The Freck term cirque originates from the Latin word circus meaning circle. They are among the most frequent types of glaciers found on Earth. They are found in half-open, semicircular shaped niches, or hollows located on mountainsides or in upper part of valleys. They are very sensitive to climate change. They are vital water reservoir. Hanging glacier. A glacier that originates high on the wall of a glacier valley and descends only part of the way to the surface of the main glacier. Avalanching and icefalls are the mechanisms for ice and snow transfer to the valley floor below. Ice cap. A dome-shaped accumulation of glacier ice and perennial snow that completely covers a mountainous area or island. The surface area is less than 50,000 square kilometers. Example: Iceland, Canadian Arctic. 12. Environmental geology. Ice field. A continuous accumulation of snow and glacier ice that completely fills a mountain basin or covers a low-relief mountain plateau to a substantial depth. When the thickness becomes great enough, tongues of ice overflow the basins or plateaus as valley glaciers. Ice shelves. They are simply the floating sections of ice sheets. Example: Greenland and Ellesmere Island have many ice shelves. Ice streams. They are fast-flowing ice channels bordered by slower-flowing ice with a velocity up to several kilometers per year. They have a slippery bed, the presence of sediments, the presence of subglacial troughs, presence and routing of subglacial meltwater. Outlet glaciers. These drain ice from caps and ice sheets, and flow beyond ice cap or ice sheet margin. In this catchment area is not clearly defined, and they form valley and troughs. The outlet glacier is confined to the narrow valley by the neighboring cliffs, and by lateral moraines deposited during a geologically recent period of glacier expansion. During that expansion, the outlet glacier reached the valley floor, cooled, and formed a Piedmont lobe confined only by its own terminal moraine. In other words, it is a tongue of ice that extends radially from an ice dome. It may be identified within the dome as a rapidly moving ribbon of ice, an ice stream, while beyond the dome it typically occupies a shallow, irregular depression. The 700 kilometers long Lambert Glacier, Antarctica, is one of the world's largest outlet glaciers. Source: Encyclopedia of Snow, Ice and Glaciers, p. 799. Piedmont Glacier. A fan or lobe-shaped glacier, located at the front of a mountain range. It forms when one or more valley glaciers flow from a confined valley onto a plain where it expands. The 30-mile-wide Malaspina is the largest in Alaska. Polar Glacier. A glacier with a thermal or temperature regime in which ice temperatures always remain below the freezing point. 13. Environmental geology. Reconstituted glacier. A glacier formed below the terminus of a hanging glacier by the accumulation, and reconstitution by pressure melting, regulation, of ice blocks that have fallen and or avalanched from the terminus of the hanging glacier. Also called glacier remini. Rock glacier. A glacier-like landform that often heads in a cirque and consists of a valley-filling accumulation of angular rock blocks. Rock glaciers have little or no visible ice at the surface. Ice may fill the spaces between rock blocks. Some rock glaciers move, although very slowly. They are lobate or tongue-shaped landforms. They have characteristics, wrinkled, patterns. The downslope movement flow of rock debris is estimated between few centimeters and decimeters per year. Transition phenomenon between glacier and non-glacier processes. Image 4. Rock glacier, James Ross Island glaciers, types of glacier. 2 types of glacier. Temperate glacier, a glacier with our temperature regime in which liquid water coexists with frozen water, glacier ice during part or even all of the year. 14. Environmental geology. Tidewater glacier, these are glaciers with a terminus that ends in a water body, like an ocean or a large lake. Tidewater glaciers are found in Alaska, the Canadian Arctic, Greenland, Svalbard, Novaya Zemlya, and the Antarctic Peninsula. Typically, tidewater glaciers calve ice to produce icebergs. The ablation is mostly by calving. Catchment glacier. The catchment glacier represents the superficial area of a glacier from where the glaciers receive and release the snow, ice material in different form and maintain the equilibrium of a glacier. The catchment of a glacier may be formed by single or more ice body, slowly moving on the downward slope and from a huge glacier reservoir system. All processes by which snow or ice are added or removed from or to a glacier are considered on its catchment basis. Source: Encyclopedia of Snow, Ice and Glaciers, page .127. 7.5 Glacial budget and mass balance. Glacial budget decided by the accumulation and ablation. If there is more accumulation of ice, it shows a glacial advance, and if more melting or ablation leads to glacial retreats. The balance between both zones of accumulation and zone of ablation decides the glacial budget. The glacier advance, when there is more snowfall and less melting in the following summer. And if there is more melting as compared to snowfall, then the glacier retreats. The equilibrium line is decided by the zone of accumulation and zone of ablation, image 5. The position of equilibrium line changes every year depending upon more snowfall or more melting. More snowfall and cooler summers favor the glacial advance, while less snowfall and warmer summer favor the glacial retreat. Mass balance B is the product of accumulation C plus ablation A. B equals C plus A. Mass balance is usually given in meters water equivalents MW E. The mass balance varies according to the time and space, as in winter more snowfall means more accumulation, while in 15. Environmental geology. Summers more melting means more ablation. Figure shows glacial mass balance. Figure A shows the relationship between the altitude and temperature. Figure B shows the surface mass balance and C shows annual net mass balance. Figure D shows the mass balance, C plus a gradient curve. Glacier mass balance is measured by staking out a glacier. This method is time-consuming and needs to visit stakes several times a year. The stakes used for this purpose can be made up of wood, plastic, or bamboo. The stakes are inserted to a known depth into the glacier. Image 5. Cross-sectional view of an alpine glacier showing internal flow lines, zone of accumulation, snow line, and zone of melting glaciers. 7.6 Glacial landforms. Glacial landforms are grouped into erosional and depositional landforms. Erosional landforms are formed by removing materials and depositional landforms are formed due to retreating of ice. Erosional glacial landforms are formed by the erosion of bedrock. Glacial striation are formed. 16. Environmental geology. Where sharp-edged rocks scrape across bedrock. The striation also tells about the direction of flow of ice, when ice disappeared from the area. The glaciers usually makes U-shaped valley, while rivers make V-shaped valley. When two U-shaped valleys are next to each other, they formed a sharp ridge called an arete. Other landforms created by erosion: airhorn, col, tarn, cirque, hanging valley and glacial trough. Sediments are deposited by glaciers and ice is responsible for large amount of erosion. When ice moves it erode and when melt, leaves behind sediments called till. The common landform of glacial deposition is moraine. A moraine is unratified and unsorted deposits of sediments formed by the grinding and erosive effect of a glacier. The grinding process produces silt and melting water carries this silt and deposits in front of the glacier called sander. Other landforms created by deposition are reglacial erratics, kettle, esker, and drumlin. Moraine: moraine is any material transported and deposited by a glacier. Like a river carries all sorts of debris and silts with its flow and creates deltas, likewise glacier carries rocks and soil and form moraine. A glacier acts like a conveyor belt and carries sediment along with it, and deposits at the end or sides of the glacier. Moraines are of different types depending upon the location as shown in image 6. A lateral moraine. A lateral moraine forms along the sides of a glacier. B. Medial moraine. A medial moraine is formed where two glaciers meet. C. Terminal moraine. Terminal moraine formed at very end of a glacier. D. Ground moraine. A blanket of glacier till deposited on all of the surfaces over which a glacier moves, typically by moving ice. 17. Environmental geology. Image 6 Different types of moraines. Source. Environmental geology. 3. Description. 3.1 Introduction. The geological processes, active on the surface of the Earth, are known as exogenous processes. They are capable of creating both constructive and destructive landforms. The geological agents play a significant role in sculpturing the Earth's surface. The geological processes like weathering, mass wasting, erosion, transportation and deposition play a significant role. The chemical and mechanical weathering disintegrates the solid rocks exposed on Earth's surface into small loose fragments so that they can be picked up and transported by wind. Wind is a powerful and effective agent capable of eroding, transporting and depositing the surface materials. Sand and dust storms are a regular phenomenon in the deserts. Environments in the desert are characterized by very high daily and annual range of temperature, very low mean annual rainfall, absence of vegetation, dominance of sand and high-velocity winds. Aeolian landforms are produced by either destructive or constructive action of the wind. The word, Aeolian, is derived from Aeolus, in Greek meaning, the god of the wind. Aeolian term is also used for all processes powered by wind. 3.2 Erosive action of wind. Wind is controlled by the seasonal variations resulting in the uneven distribution of solar heat over the surface of the Earth. Thus the circulation of air makes the wind to blow, and moving air is termed as wind. The action of wind can transport huge quantities of windblown material to great heights and many kilometers. Wind is a turbulent fluid and transports sediment. We can compare wind action with running water, though wind flows at a greater velocity than water. Sand, clay and silt particles can be carried as the suspended load by the wind as it has lower density. While the larger particles move along the ground as bed load. Wind is considered as a very effective agent of erosion and deposition like water. The wind exerts the same kind of force on particles on the land surface that a river exerts on its bed. The wind velocity and surface roughness are the two factors that primarily control the power of wind to erode surface particles. The erosive force increases exponentially with the increase in wind. 5. Environmental geology. Velocity. As the result, the fast winds are capable of causing much more erosion than slow winds. The roughness of the surface at ground level plays an important role in controlling the nature of wind erosion. The moisture affects and slows down the action of the wind. Therefore, the water table is regarded as base level for erosion of wind. Boulders, trees, buildings, shrubs, and even small plants like grass and herbs can increase the frictional roughness of the surface and reduce wind velocity. Vegetation can also reduce the erosional effects of wind by binding the soil particles to the roots of plants. Aeolian or aeolian erosion are the terms used for wind erosion. It is performed by processes, viz. Deflation, abrasion and attrition. Wind transports sediment and modifies the landscape through these processes of abrasion and deflation. Deflation. The term deflation is originated from the Latin word, deflare, means, to blow away. The surface of any desert is covered by diverse type of fragments of rock, sand, soil and dust. Deflation involves the picking up or lifting, blowing and removal of fine and dry particles of loose sand, silt and soil from one place to the other by wind. The blowing wind picks up the sandy and fine-grained materials, and leaves the coarse. As the result, the fast winds are capable of causing much more erosion than slow winds. The roughness of the surface at ground level plays an important role in controlling the nature of wind erosion. The moisture affects and slows down the action of the wind. Therefore, the water table is regarded as base level for erosion of wind. Boulders, trees, buildings, shrubs, and even small plants like grass and herbs can increase the frictional roughness of the surface and reduce wind velocity. Vegetation can also reduce the erosional effects of wind by binding the soil particles to the roots of plants. Aeolian or aeolian erosion are the terms used for wind erosion. It is performed by processes, viz. Deflation, abrasion and attrition. Wind transports sediment and modifies the landscape through these processes of abrasion and deflation. Deflation. The term deflation is originated from the Latin word, deflare, means, to blow away. The surface of any desert is covered by diverse type of fragments of rock, sand, soil and dust. Deflation involves the picking up or lifting, blowing and removal of fine and dry particles of loose sand, silt and soil from one place to the other by wind. The blowing wind picks up the sandy and fine-grained materials, and leaves the coarser fragments behind to form stony and rocky deserts. Abrasion. This involves mechanical scraping, rubbing, grinding, polishing and abrading of a rock surface by friction between rocks and moving particles during their transport by wind. In this process, the individual grains may shed off some of its weight and shape and attain more roundness on grinding off their angularity. The particles transported by wind can strike the obstructing materials along its path called corrosion. The process of corrosion can carry out grooving, scarring, polishing and grinding of rocks. Its intensity depends on the size and density of carrying materials, and also the Earth's surface rocks. Attrition. When the load sediments undergo wear and tear due to mutual impacts during the process of transportation by wind resulting in further reduction in size is known as attrition. 3. 3. Velocity. As the result, the fast winds are capable of causing much more erosion than slow winds. The roughness of the surface at ground level plays an important role in controlling the nature of wind erosion. The moisture affects and slows down the action of the wind. Therefore, the water table is regarded as base level for erosion of wind. Boulders, trees, buildings, shrubs, and even small plants like grass and herbs can increase the frictional roughness of the surface and reduce wind velocity. Vegetation can also reduce the erosional effects of wind by binding the soil particles to the roots of plants. Aeolian or aeolian erosion are the terms used for wind erosion. It is performed by processes, viz. Deflation, abrasion and attrition. Wind transports sediment and modifies the landscape through these processes of abrasion and deflation. Deflation. The term deflation is originated from the Latin word, deflare, means, to blow away. The surface of any desert is covered by diverse type of fragments of rock, sand, soil and dust. Deflation involves the picking up or lifting, blowing and removal of fine and dry particles of loose sand, silt and soil from one place to the other by wind. The blowing wind picks up the sandy and fine-grained materials, and leaves the coarser fragments behind to form stony and rocky deserts. Abrasion. This involves mechanical scraping, rubbing, grinding, polishing and abrading of a rock surface by friction between rocks and moving particles during their transport by wind. In this process the individual grains may shed off some of its weight and shape and attain more roundness on grinding off their angularity. The particles transported by wind can strike the obstructing materials along its path called corrosion. The process of corrosion can carry out grooving, scarring, polishing and grinding of rocks. Its intensity depends on the size and density of carrying materials, and also the Earth's surface rocks. Attrition. When the load sediments undergo wear and tear due to mutual impacts during the process of transportation by wind resulting in further reduction in size is known as attrition. 3.3 Erosional landforms. We will discuss the various erosional landforms resulting due to above-mentioned processes. Desert pavement. It is a typical desert surface covered with closely packed, interlocking angular or rounded rock fragments of pebble and cobble size. They are formed by gradual removal. 6. Environmental geology. Of sand, dust and other fine-grained material by wind and intermittent rain. Wind blows away finer particles like clay, silt and sand on deflation leaving behind the bigger fragments. Boulders or pebbles are too large for wind to transport. Accumulated coarser material, having fairly smooth shinning surface, are left behind as desert pavement, figure 1, also known as lag deposits. It marks the maximum limit of aeolian activity by deflation. Desert pavement, also known as stone pavement, forms a coarse gravelly ground surface that protects the soil or sediments below from further erosion. Figure 2, fine-grained particles are blown by wind. Wind blows away finer particles leaving behind pebbles and boulders resulting in desert pavement. Deflation basins. They are depressions formed in the deserts due to removal of sands to a greater extent. Deflation by strong wind scoops out sand-sized particles producing shallow depressions of varying shapes. This may cause depression sometimes with its base touching quite depth. These evacuated depressions are up to 1.5 kilometers long and a few meters deep, figure 2. These blowouts when intersect the water horizon, they get partially filled with water, resulting in development of swamp or oases. Deflation basins also commonly develop where calcium carbonate cement, in sandstone formations, is dissolved by groundwater, leaving loose sand grains that are picked up and transported by the wind. Large deflation basins, covering areas of several hundred square kilometers, are associated with the greatest desert areas of the world, particularly in Sahara Desert. 7. Environmental geology. Figure 2, deflation basins are produced by the evacuation of sediment by wind. Mushroom table or zugans. Wind abrasion erodes the underlying soft rocks more rapidly than the hard rocks, resulting in the formation of mushroom table. This results in the formation of horizontal ridges with top of hard rocks, having low dips and joints which are parallel to the prevailing winds, figure 3. This resembles ridge and furrow structure, also known zugans. Figure 3, block diagram showing mushroom table. 8. Environmental geology. Pedestal rocks. They are the exposures having broad upper part and narrow base carved by the action of wind over an existing standing rock mass. The heavier and larger particles remain near the ground and only smaller lighter particles move above with the wind at higher level, which results in the formation of pedestal rock. When the larger particles strike the homogeneous rocks, they differently abrade the upstanding rock mass such that rock head or cap balances over a very slender neck, resulting into a pedestal fan-like shape. Differential erosion is the term used for varying resistance to the agencies of erosion wherein parts of softer rock are removed to a greater rate than the harder one. Thus wind abrasion plays a significant role in shaping pedestal rocks and is also called as mushroom rocks, figure 4. 9. Environmental geology. B. Figure 4, sketch showing differential erosion resulting in formation of pedestal rock. Field photographs of pedestal rock from Thar Desert. Yardangs. Yardangs are sculptured landforms extending up to tens of meters high and kilometers long. They are streamlined hill, carved from bedrock or any consolidated or semi-consolidated material by double action of wind abrasion and deflation, figure 5. When viewed from above, yardangs resemble like the hull of a boat, exhibiting commonly asymmetrical shape and elongated leeward tails. This is perhaps because of slight variation in wind direction. Yardangs are composed of cohesive silts and clays, sandstone, or limestone and develop in regions with strong unidirectional winds. Yardangs are classified as mega yardangs, meso yardangs and micro yardangs on basis of size. Mega yardangs can be of several kilometers long and hundreds of meters high. Meso yardangs are generally a few meters high and 10 to 15 meters long. Micro yardangs are only a few centimeters high. 10. Environmental geology. Figure 5, stages of development of yardang. Ventifacts. They are produced by wind abrasion on boulders and rock surfaces. Ventifacts are rocks that have been abraded, pitted, etched, grooved or polished by wind-driven sand. The changing and prevailing wind direction shapes different facets along sharp ridges to transform rounded stones to angular ventifacts, figure 6. Figure 6, stages of formation of ventifacts. 11. Environmental geology. Blowouts. These are broad shallow caves in hills formed due to wind erosion. The sand grains are the most effective agents of abrasion. Rocks exposed to the sandblasting by prevailing winds become pitted, grooved, and polished, figure 7. Figure 7, field photograph of blowout, Thar Desert. Desert varnish. It is a dark coating on rocks found in arid regions, composed dominantly of fine-grained clay minerals containing black manganese oxide and red iron oxide. Desert varnish forms only on physically stable rock surfaces that are no longer subject to frequent precipitation, fracturing or sandblasting. 3.4 Transporting power of wind. The stages of transportation depend on the wind velocity and sediment load. Wind has the ability and force to lift the Earth's unconsolidated sand, silt and dust-sized particles by the mechanisms mentioned like saltation or rolling and traction and suspension, figure 8. 12. Environmental geology. Saltation. This process involves the lifting of heavier and coarser sediments such as sand grains, pebbles and gravels, etc. Only for short distance and for smaller heights above the ground periodically during high wind velocity. This movement takes place close to the Earth's surface and the picked up and lifted materials may be dropped and picked up again and again during the process of transportation. The lifted particle fall and they transmit an impact to another stationary particle resting on the ground. The size and shape of the grain control the height and distance to which these sediments are transported in one cycle. The heavier particles and massive rock fragments are transported by dragging or rolling along the ground called traction as bedload. Suspension. The silt and clay-sized particles are carried in suspension, above the ground surface. The suspended grains travel thousands of kilometers and reach to great altitudes. The force of the wind lifts clay and silt particles of lighter density from the ground and carries high up to upper layers. This is called suspension because the particles once lifted are not allowed to rest on the ground again till the velocity of wind in those upper layers is checked. Figure 8 Suspension, saltation and traction or rolling. 13. Environmental geology. 3.5 Deposition by wind. Wind carries forward sediments and particles once picked by it from any source on the surface for a varying distance depending on its carrying capacity. Deposition of material carried away by wind can take place at any place and time. The settling and deposition of wind-borne material takes place when there are obstructions. All these create constructive aeolian landforms. Wind is an effective agent for sorting of materials according to their shape, size and weight. Decrease in velocity of wind results in deposition of wind-blown sediments which are highly sorted in nature. Wind deposition can take place due to following reasons. Obstruction in movement of wind like hill, mountains, buildings, forest belts, vegetation, etc. Reduction in wind velocity, an increase in moisture content and precipitation, rainfall and snowfall. 3.6 Depositional landforms. Let us discuss the following depositional landforms formed by wind action. Loess. Loess is aeolian sediment, clastic in nature formed by accumulation of wind-blown sediments predominantly of silt size. Clay along with silty fractions are deposited as loess. Loess is pale yellow or buff in color, homogeneous, friable, porous, slightly coherent, typically non-stratified and often calcareous, figure 9. Its grains are angular with little polishing or rounding and are composed of quartz, feldspar, mica, calcite and other minerals. Loess is mainly derived from three main sources: deserts, river floodplains in semi-arid regions and Pleistocene glacial outwash deposits. Loess is formed by accumulation of wind-blown dust picked from outwash plains, exposed by repeated advances and retreats of continental glaciers. Loess is stabilized by moisture and vegetation in order to accumulate. These deposits create rich soil, e.g. Loessic deposit in northern China which is about 300 meters thick. Loess ridges that have formed or aligned along direction of prevailing winds during last glacial period, maximum in several areas of the world and are called as Pahar ridges in America and Greta ridges in Europe. Their formation has been explained by a combination of wind and tundra conditions. Loess is a result of its unconsolidated. 14. Environmental geology. Nature is easily eroded and therefore loessic areas are characterized by steep cliffs and rapid lateral and headward stream erosion. Figure 9 Loessic sediments deposited over quartzites of Delhi Ridge. Playa. Water sometimes collects in flat area called playa at bottom of desert basin resulting in formation of an oasis. When playa deposits have more saline matter and salts then it is known as salina. As already mentioned, oasis may be produced when bottom of a basin intersects with groundwater. Sand dunes. When you think of sand dunes and dune fields, you are reminded of deserts, figure 10a. Dunes are of variable heights such as 100 to 300 feet or more depending on transporting power and available material. Many dunes grow up to the height as much as 300 meters. The conditions required for formation of dunes are abundant supply of loose sediments, i.e. sand. Sufficient energy to move sediment, i.e. wind velocity. Obstacle around which sand accumulates, i.e. cliff, amount of vegetative cover, and dry or arid climate. 15. Environmental geology. Sand dune is a mound or ridge of sand deposited with a crest, figure 10b. Dunes are not permanent structures. A sand dune often moves or migrates forward windward from one place to the other in desert region. However, grasses anchor the dunes with their roots and hold them temporarily in place. If dune is devoid of vegetation, winds can regularly change its form and location. An ideal dune has a gentle windward slope of about 10 to 15 degrees and much steeper leeward slope of 30 to 35 degrees. Wind lifts sand grains from windward side and drops them on leeward side, also known as slip side, and consequently the migration takes place. Dune advances by movements of individual grains of sand has been observed in Thar Desert. Structures of static and migrated dunes are shown in figure 11. A. B. Figure 10, a dune field in Thar Desert. B. Sketch of a dune. 16. Environmental geology. Figure 11 Migration of dunes. Types of dunes. Dunes are classified into 5 principal types, namely Barchan, longitudinal, transverse, parabolic and star dune. The size, shape, and arrangement of dunes depend on interaction of factors as sand supply, direction and velocity of prevailing wind, and amount of vegetation. Barchan dunes are crescent-shaped dunes with 2 tapering horns pointing windward and steep slip face on concave side, figure 12. They are generally flat with dry surface and little vegetation, a limited supply of sand, and a nearly constant wind. Barchan dune consists of well-sorted, very fine to medium sand. They form when wind blows constantly in one direction. These dunes migrate when sand slides down the leeward slope and sand moves up the windward side. Such movement of sand grains produces a series of crossbeds that slope in direction of wind movement. Barchan. There are following 3 types of desert. I. Rocky desert consists largely of barren, hard and rocky plateaus and plains that have very little amounts of sand, e.g. Sahara. E. Stony desert constitutes rocky waste, e.g. near Srikalia G. Bikaner. E. Sandy desert is essentially composed of sands, poor vegetation, e.g. Pokhara, Rajasthan. 17. Environmental geology. Are usually small, with the largest reaching about 30 meters high. Barchan are the most mobile type of major dune types. Figure 12 Barchan dune. E. Longitudinal dunes, also called safe dunes, consists long, linear or slightly sinuous sand ridges aligned, generally much longer than wide, parallel to direction of prevailing winds. Long axis of sand ridges is parallel to direction of net sand movement. They form where sand supply is somewhat limited. Figure 13. Sediments in longitudinal dunes are well sorted with grain size varying from very fine to medium grain sand. Longitudinal dunes result when winds converge from slightly different directions to produce the prevailing wind. They range in height from about 3 meters to more than 100 meters, and some stretch for more than 100 kilometers. The longitudinal dunes cover extensive areas in Saudi Arabia, Egypt, and Iran. Figure 13 Longitudinal dune. 18. Environmental geology. E. Transverse dunes form long, wavy, linear ridges perpendicular or transverse to the prevailing wind direction in areas that have abundant sand and little or no vegetation. Figure 14. In plan view, transverse dunes have a wave-like appearance and are therefore called sand seas. The dunes may be as wide as 3 kilometers with crests of as high as 200 meters. The intermediate form of dunes known as barchanoid dunes develop when barchan forms separate into individual barchan dunes along edges of dune field. Sediments in transverse dunes are very fine to medium sand and are well sorted. Wind speed should be constant, moderate and unidirectional. Figure 14 Transverse dune. IV parabolic dunes are most common dunes occurring in coastal areas where there is abundant sand supply, strong onshore winds, and a partial cover of vegetation. Figure 15. Parabolic dunes have a crescent shape like dunes with their tip pointing upwind. Parabolic dunes form when there is abundant supply of sand and vegetation cover is broken and erosive action by deflation creates a deflation hollow or blowout. As the wind transports sand out of depression, it builds up on convex downwind dune crest. Central part of dune is excavated by wind, while vegetation holds the ends and sides fairly well in place. Sediments comprising parabolic dunes are very fine to medium and well sorted. 19. Environmental geology. Figure 15 Parabolic dune. V. Star dune is commonly found in the deserts of North Africa and Saudi Arabia. Star dune is so named because of its resemblance to a multi-pointed star. Figure 16. It is pyramid-shaped with 3 or more arms radiating from a peaked center, and they develop where wind direction is variable. They grow taller rather than migrating. Star dunes are sometimes more than 100 meters above the surrounding desert plain. Star dune comprises very fine to medium sand. Star dune for its formation requires wind blowing from several different directions. Figure 16 Star dune. 4. Summary. In this lecture we learned about processes controlling wind erosion and resulting erosional landforms, transportation of wind-borne sediments, depositional landforms like losic deposits and sand dunes, types of sand dunes. 20. Environmental geology. 19. Environmental geology.